Hello, welcome to the Graphing Techniques for One Variable screencast. So what we're going to be covering in this screencast is the 5-number summary. I'm going to review the 5-number summary, the 1.5 IQR rule, how we determine outliers. We're going to talk about some graphical representations, and I like these a lot because they help reveal patterns in data, and they're kind of the first thing I do when I get new data. And so a name for that, if you want to be fancy, is exploratory data analysis. The graphs we're going to look at are going to be an index plot, and that's where each value in the variable is displayed in the order in which it appears. So the order, if it's the first number, its x value is 1. If it's the fifth value, its x number is 5. That's the index. Then we're going to do a stem plot, and a stem plot is kind of cool. It's a text-based way to describe numeric data. You'll see how that goes. If you've seen a histogram before, it's kind of like that, except there's a little bit more information. A histogram breaks values down into groups of equal size, and it counts how many are in those groups. You'll see how that works when we get there. Finally, we have box plots, or not finally, but we have box plots, and box plots are going to use that 5-number summary that we talked about in the last screencast, and that I'll review again in just a second, or I'll review when we get to the box plot section. And then you have bar plots. And bar plots, although technically requiring numeric data, if you have categorical data, you can frequently tabulate that data and turn it into numeric data by counting the number of things. And so then you make a nice bar plot. All right, so let's start with the index plot. You use this on numeric variables. And as I've said, the value of the variables are in the order in which they occur. So if I have a 26 in the first place, it has a height of 26. And if I have a 25 in the second place, it has a height of 25. All the way to my last value, which is in the 10th place, that has a height of 26. So I use the R command plot, and I apply it to a variable, and that variable holds the data. Now if I want to be fancy, I can use plot with some named arguments. So the first argument is the data, and then I can give it a title, and that's called main equals. I can control the color, sky blue. I can set the character expansion, that makes the dots bigger or smaller. And then I can set the plotting character. So 20 is a nice solid dot. So I like those, and those are good examples. Okay, so that's an index plot. Stem plots. Now this is maybe the most complicated one to explain, but once you get the hang of it, it's useful and versatile, and it's the kind of thing you can do in a restaurant without having a computer, which is nice. So I have some data. These are vitamin D levels of various, I forget if it's girls or boys, taken from middle school. Every value gets assigned a stem and a leaf. So you have to make a choice. So here I'm going to think of the tens places, and that's going to become my stem. So the stem for 16 is 1, and the leaf is 6, the ones place. For the number 23, the stem is 2, and the leaf is 3. The number 26, the stem is 2, and the leaf is 6, so on and so forth. So when you're doing a stem plot, the leaves, or I should start with the stems are drawn over here on the left, and then you have a vertical line. And then the leaves get drawn over on the right. So 16 is represented in this stem plot by the 6. On the row for the stem 1. 23 has a stem 2, its leaf is 3, so you have a 3 there. These aren't in any particular order right now, but typically your first step is to put them in order. 25, so the leaf is 5. 26 is the next one. The leaf is 26, and so on and so forth. So a couple things to notice. The stems are written on the left. The number of entries on the right is the same as the number of values that you've recorded. 1, 2, 3, 4, 5, so on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and so on. Now I'll point out there are no numbers that are in the 50s in this data set, and it is just as important to show what's not there as it is to show what is there. So that's important. One other thing I should comment on is the order of the leaves is sorted. So, and it's sorted as you move away from the stems. So 23, 25, 26, 28. Now, when you make a stem plot, you start by choosing a scale. You choose a position that's going to be your stem, and then that determines what your leaf is going to be. So for example, I could choose the hundreds place to be the stem. So then the leaf is 6. And the stem and the leaf. And the stem and the leaf. And so on and so forth. Now I want to point out that if you compare this data set to the last, they're quite different, 16, 23, 26, 160, 230, 260, but the stem plots look exactly the same. Let me try drawing that again. There we go. And I bet, right? So you can't tell about the scale of the original data just from looking at the stem plot. Now the other question is, what happens if you have other information? So in this data set, I have it's 161. So if I wanted to use the hundreds place as the stem and the tens place as the leaf, I have to decide what to do with the extra information. And there's two basic strategies. One strategy is called rounding. And so I would round the appropriate place. And I have some examples in the table. So 161, if 10 is going to be my leaf, the tens place is my leaf, then I would round 161 to 160, and 6 is my leaf. 239 rounds to 240, 4 is my leaf. 261 rounds to 260, 6 is my leaf. Now trimming's even easier. You just get rid of the last digits. So if I get rid of the 1 in 161 on the right, I get 160. 6 is my leaf. 239, get rid of the 9, 230, 3 is my leaf. So they're almost exactly the same. Let's see what they do. So in this example, I wanted to show you the R. This is the original data set, and I wanted it there. The problem is R doesn't have a nice way to trim, so I had to actually trim it myself. So 161 trimmed to 160, 239 trimmed to 230, 261 to 260, and so on. And then I just used the R command stem. So this is what a stem plot would look like if I had trimmed. Now, by default, R uses rounding, and that's fine if you're doing it using R. You're allowed to do that. And so I just used the stem command. And so remember, 161 trimmed or rounded came to the same thing, and in both places we have our leaf of 6. On the other hand, 239, that when you trim, that becomes 230, so the leaf is 3. So we have a 3 over here. But if I round 239, it rounds to 240, so we had a 4. But notice the shape doesn't look particularly different. In this case, not different at all. It's just the numbers in there are a smidge different. So you still get the basic idea of the distribution, what values are possible and how likely they are to occur. Now, if you want to make these things by hand, and you will want to at least once, you typically start with some data, and then you need to sort that data. And if you're careful about how you organize it when you sort it, you basically make the stem plot just as a matter of course. So if I took all the numbers that started with 10 and sorted them, I get 16. If I took all the numbers that started with 20 and sorted them, 23, got a 26, and a 25, and a 28, and I put them in sorted order, 23, 25, 26, 28. Now notice on the stem plot, you have 1 and the 6, you have 23, 25, 26, and 28. Like I say, they practically sort themselves. And you have to think carefully about, whether you're going to trim around, but most of the time it's not a big deal. Now sometimes, as you can see in this data set here, maybe I'm worried that I'm missing some information. And so if I want to expand the stem plot, I can do what's called splitting the stems. So the basic rule is that every stem is written twice. There's a little caveat to that. We'll get to that. The first occurrence gets leaves 0 to 4, and the second occurrence gets leaves 5 to 9. So I'm going to start with the 2 here. I have 23 and 25, 26, and 28. The 2, That first 2 gets all the leaves between 0 and 4. That 2 gets all the leaves from 5 to 9. The 3, the cutoff goes here. 3, the first 3 gets the leaves 3 and 4. The second stem 3 gets 5, 5, 6, 7, and 8. And so it kind of spreads things out. Now, if I were being very careful about this, I might have written a 1 here and a 6 here, but you can omit those if they're empty, right? So there's no reason to write the first one if it doesn't have any values. That you don't lose anything by leaving that off, and you don't have to write the last 6 if it doesn't have any values either. You don't lose anything that way. So I hope that's clear. Now, on this on the slide deck, I gave you sort of an at-home exercise. So I gave you some data, and the answers have the text in white. So if you take, the first thing I said is sort and organize. So if you take your mouse and you highlight it, you'll see what happens when you sort and organize it. And then you can look at the stem plot and so on. So this is a chance for you to try it out yourself and make sure you know what's going on. Now when you're doing it, a few things to be careful of. Don't use commas or spaces between the leaves. That ends up being misleading. So if I were creating a stem plot and I had, say, a 0 and a 1 as some stems, oops, let me try that again. A 0 and a 1, and there's my separator. And maybe this was a 1, and then I had a 2 and a 3. Notice if I put a space there, this looks a lot bigger than that. And so that's misleading. Whereas if I space them out appropriately, and that's why you should always use a monospaced font as well, then that is twice the width of that. And so it's an accurate representation of the number of things in the category. So finally, I can use R scale equals 2 to force the split, which I didn't show the code here, but that's what I did. We'll see that on the next slide. So let's suppose I'm considering 2 different sets of data and I want to compare them. One way I can do that is with a back-to-back stem plot. So with the back-to-back stem plot, I do 2 stem plots. So first I'll do the vitamin D values for the boys and then for the girls. And just by directly comparing them, you can already see some differences. So the stems, if nothing else, on the girls are higher, right? Ranging from 1 to 5. The stems on the boys range from 0 to 3. There's a lot more concentration in the boys' vitamin D levels, around the 20s, and the girls are more spread out evenly between the 30s and the 40s. So you can already see differences in the center and the spread. So if I want to compare them directly, first I wanted to split the stems because I thought that would be more informative. So again, I use scale equals 2 to force them to split. And then I just wrote them next to each other. Now notice 0, 8, 1, 2, 1, 6. I still order the leaves numerically, but moving away from the stems. Okay, so that's the basic idea there. Now when you're working on your assignment, let me switch over to that, you have to make a back-to-back stem plot. So if I were over in assignment 1, scrolling down, let's see, so here's some fasting plasma glucose levels, and I'm supposed to make a back-to-back stem plot or side by comparing the class and individual instruction groups. So this group was individual instructions, and these guys here were the class, I believe. Oh, here they are. Yep, 5 months after the end of the class. Okay, so first off, how am I even going to get these into R? Now, I have hints on the screencast for this assignment that show you how to do that. So I'm not going to replicate that here because I want to keep this a little bit more focused. But if I were just going to work in the console, I could have glucose 1, and I could do scan. Somebody had asked on the readings, how do I know which scan to use? It's numeric. I just do scan as is. There's the data. I just paste it in. I hit enter. couple times. And if I look, I can verify that glucose 1 does contain the values that I want. And then I can take the values from glucose 2, copy and paste them in. I can do a stem plot of glucose 1. I can do a stem plot of glucose 2. And you can already see some differences. The stems go from 0 to 3 on the first set, from 1 to 2 on the second set. Now it gets a little bit tricky, it gets a little catchy if I try to split it here. So I don't think I'm going to do that command on glucose 2. But it works fine on glucose 1. So if I were entering these in, so maybe, let's see, that was glucose 1, right? That was the class. And these were the individual. So my stems start from 0, and based on all of this I have to go up to 3, and I see a 3, 6 there. So it looks like I have a 0, a 1, a 1, a 2. I'm not going to do the whole thing again because I've done this in the assignment thing, but you get the idea here. And then so for the zeros, this could be an 8, 1, 2, 3, 1, 3, 4. You see how that works. When I'm putting the other ones in, I might as well just do it straight off the first one. I have 1, and again I have to put them in backwards. 3, 3, and then 1, 2, 3, 4, 5. I see 5 6s and a 9. So the 9 goes on the outside. Oh, and if I'm splitting stem, nope, that's good. 5 6s and, oh, it already split it, that's why. 5 6s and a 9. 5 6s and a 9. Now, I like to get rid of the space between them. I think they should be right up against each other. Our defaults is something else. So you may have to play a few games like that. And I also like these spaces to be the same as well. That makes it a little bit tricky with the stem on the top, but maybe I'll just replace it with that. There we go. Anyway, so you finish entering all those in, and then when you knitted it, those triple backticks there on both sides make it look and behave quite nicely. So when you're done entering it all in, you get a nice back-to-back stem plot. So that's kind of handy. Going back to our main discussion, now we want to talk about box plots, and that's where we need to remember about the 5-number summary. So remember, the 5-number summary was the minimum, the first quartile, the median, the third quartile, and the max. So the value of Q1 ends up being this horizontal line. The value of the median is this horizontal line. And the value of Q3 is the height of this horizontal line. So that's kind of handy. I have the calculations on the next slide, so we'll deke over there and look at them in just a second. Let me do that now. And I'll talk about the whiskers in just a moment. Let's see what we got here. So I'm going to use R to make my life easier. I'm going to use the summary command. First quartile 23.75, third quartile 29.5. The IQR is the difference, 5.75. I can calculate my thresholds. Q1 minus 1.5 IQR. Q1 was 23.75. The IQR was 5.75 times 1.5, taking the difference, 15.125. So the upper threshold, Q3 plus 1.5 times the IQR, that's at 38.125. So if you look at this, the highest non-outlier, right? The upper threshold is at 38. If I go back and I look, my highest value is 37. This is the height of your highest non-outlier. This is your lowest non-outlier. So it's the lowest thing that's not below 15.125, and that ends up being a 16. I have a value of 8 and a value of 12. They're outliers, so they're drawn as bubbles. So again, looking back over here, we have the data. So I put that data in order. I would calculate Q1, M, and Q3. I draw all my nice horizontal lines. Again, Q1, median, Q3, highest non-outlier, according to the 1.5 IQR rule, lowest non-outlier, not the threshold, but an actual value. So these things are actually representing true values in the data. And then bubbles are anything that are outliers. There may be none, there may be lots. And that's how you make a box plot. Now, side-by-side box plots are a piece of cake. It's great. So once the data is in R, which I've already done, I use boxplot. I do list. I name the first, I name the second. I tell you the variable. And so we get the box plot for the boys, we get the box plot for the girls. You can compare and contrast that. Now bear in mind we drew our stems with a small number on top, so the fact that this looks higher is somewhat misleading. Right? Here's 20, here's 30. Here's the 20s. Here's the 20s. And here's the 30s. But again, you can directly compare and see quite quickly that the distribution for the vitamin D levels in boys are different than the distribution for the vitamin D levels in the girls, and their centers are different, and the spreads are even different, and it's a little more quantified here. Okay, so the next graph on our tour are histograms. So we'll use the same data sets. And we're going to break them up into equal-sized intervals, 10 to 20, 20 to 30, 30 to 40, 50 to 60, 60 to 70. So how many of the values are between 10 and 20? Just one of them. How many are between 20 and 30? I put them in order here, so 1, 2, 3, and 4. How many are between 30 and 40? Now, this is where it gets a little bit tricky because you have to make a choice. So we have chosen, using algebra notation, the smooth parenthesis means don't include, the hard parenthesis means does. So we don't include 30, but we go up to 40. We don't include 50, but we go up to 60. We don't include 60, but we go up to 70. Now, let me make sure that this all makes perfect sense. I think I put the wrong, let me pause and check. Yep, so there was a small typo, since fixed. So 40 to 50, there are 6, 50 to 60, there is 1. So 40, not including the 40, 1, 2, 3, 4, 5, 6, and then we have 1 from 50 to 60. Now R chooses its own breakdown points, and so you see it's actually going from 15 to 20, 20 to 25, 25 to 30, and so on. So the numbers look a little bit different here. Now I can force it by telling it where I want the breaks to occur, and it looks like I still have this typo over here as well. So I'll fix that in the final one. This should be 40 to 50, and this should be 50 to 60. Now, all I'm saying is you can either count directly, where you actually count how many, or you can do frequencies. So you divide, there were 20 observations total, 1 divided by 20 is 0.05, 4 divided by 20 is 0.20, and so there you'd use the frequency equals false to display the counts. So let's look at the two side by side. If you're not looking closely, they actually look exactly the same. But if you look at the numbers, you can see here it says frequency and it goes from 0 to 8. Over here it says density and it goes from 0 to 0.04. So it's just whether or not you're labeling things in terms of percentages or you're labeling them in terms of actual counts. That's the only difference. And again, this is kind of cool, I should point out. So here, we're assigning a bunch of numbers. We're using that C construction, numeric stuff. Here we're using a logical value, frequency is false, and for main we're using a character value. So those are the three different sort of data types that we've really talked about in R. So I just want to reinforce that that's happening. And again, I think once you get used to it in practice, it all makes perfect sense. Okay, finally, bar plots. Like we say, categorical data isn't numeric itself, but you can make a frequency table, much like we showed with the histogram, except now you're just counting values. So you might look at the market share for Garmin, and it has 47% of it. TomTom has 19, Magellan 17, Mio 7, and the others have 10. And so what makes this a bar plot is the fact that we label the bars with the categorical value that comes from the first column. So not terribly difficult in that sense. Now I have this other example where I get a little bit fancier. I have the percentages lined up. I do want to say that you might have a table where you don't actually have the numbers associated with the categorical. You only have the categorical. And then you might go through and just count up the number of times each thing occurs, and then that becomes the height of your table. But, so here I have my percentages. Here I have company. Now, if you name the percentages, and you might want to review the webcast on R for that, then when I bar plot them, everything just works out automatically perfect, right? I don't have to do any other work, which is really nice. So here I'm setting the title. Here I'm overriding the Y label, so it says percentage. It says percent. So it says percentage. The X label says company. It's a little cut off on here so you can't quite see it. I'm setting the colors to be sky blue, spring green 1, sienna, rosy brown, slate gray 4. So I get these nice different colors. And then I have legend is true, so it tells me in a second way that Garmin is sky blue and TomTom is spring green and so on. So histograms and bar plots are in some ways very similar. They both use the y-axis to represent counts or frequencies. The histogram's x-axis, however, is numeric, and it has a numeric meaning. The bar plot, the x-axis, typically isn't. Now, if it's an ordinal categorical, then yes, maybe. So you might have a first place, second place, third place. So that can happen. But usually there's no natural order to what you're seeing. Like there's no reason to do Garmin before TomTom, before Magellan, before Mio. Sometimes you'll do what's called a Pareto plot, where you'll actually do the biggest number first and work your way down. That's useful as well. But it's all kind of basically the same thing. Usually a histogram has no space between the bars and a bar plot does, but you can break those rules if you want. Okay, that's the last thing I wanted to cover. Thank you very much for listening.